Monads for the last sort of 2 years. 2 years ago, everyone told me this was impossible and like can never possibly work, and I always was frustrated by that, and so figured I think this is the way the program is going to look in 30 years, and I figure the best time to do that is now, especially because like Haskell is always 30 years ahead, right? So why not? So this is an old talk I've given. It's not exactly up to date, especially after seeing Nick Wu's talk yesterday, where he showed a bunch of technology that I'd love to put into this library and was sort of blindsided by. But so this is Polysemy chasing performance in free monads. My name's Maguire. Here's some things about me, and the slides are available online if you want to catch them there. So I used to work at a Haskell company, and it was originally, there were no engineers. It was entirely contracted out, which is probably why it was a Haskell code base. But the Haskell programmers there, I don't think were necessarily Haskell programmers. They wrote Haskell, but it was just this like huge I/O spaghetti ball of just nothing was testable. So we didn't really test anything. But we had maybe 100,000 lines of code, and eventually there was this tension where we couldn't test anything, and so we would sort of rely on code review, and that would sort of work until it stopped working. And one day, a coworker of mine pushed some code that started like leaking millions of dollars a day, and which is a lot of money to a startup, right? And so I've always sort of thought that technology is not just sort of for fun and because like we like to be intellectually stimulated, which I think is a big part of why we do Haskell. But on the other hand, it can also help like business, and it can help keep our jobs and write better software, right? So especially when like lots of money is on the line, it's really valuable that we can we don't have these terrible bugs. So that brings me to free monads, which I said I think is what programming is going to look like in 30 years. The high-level approach is we want to be able to write like a very, very specific domain-specific language, which is like exactly right for our purposes. And then we can write our application logic against that, and then sort of ignore all the implementation details. That's not to say like we can entirely ignore those things, right? Eventually there is some code that needs to be run by the computer, but that's not to say like we should always be aware of those things. I sort of dream of this world in which a business person who is well versed in sort of Haskell syntax, but not necessarily anything else, can be productive. And like without knowing how to program, they can be productive and they can encode the business logic that they want. So that's sort of the motivation here. It turns out like most programs that we write are actually really easy to describe, right? Usually it's like we take data from somewhere, we like transform it somehow, and we push it somewhere else. None of us are doing all that interesting things, right? You just connect a bunch of services together, and that's your program for the most part. And so like there's all these bugs, but they never happen at sort of the high level. They happen in the weeds when you sort of need to connect to a database, and like what happens if that thing fails, or like what if your service is down, right? All these things that the business people don't really care about, and aren't really part of the high level understanding of the program. And so what I'd like to do is if we can take all these implementation details and we can put them in library code rather than sort of sprinkling them all the way through our application, then this gives us this sort of powerful framework for not only is it sort of easier to reason about, but it also means we can reuse the implementation details, right? A lot of times you sort of lose reusability because your application code like needs to connect to the database every time. But if you could like just move that stuff out, if you could put all that error handling sort of in a transformation layer, then you just connect that part again to the next application. And so most of your programs, once you have enough library support, are like 10 to 15 lines of code. It's sort of the dream. So this is a real program I wrote, which we had this data ingestion service, and it would read like encrypted CSV files off some weird server somewhere. And then we would like stream them off to some API call, but we'd have to batch that because it was cheaper to send like 500 requests than to make 500 API calls, or like one API call with 500 requests in it. And then we'd also have to like keep track of all that sort of for auditing purposes, and we'd store that in Redis. And this is what the program looked like. It's like really simple, right? We say like I have some way of getting records, I have some way of outputting records, and I have some statistics. And then I have some monadic code, which pulls a record through this input function. Maybe there's more records and maybe there isn't, right? If there's no more records, I just produce nothing. And if I have a record, then I output that, and then I process the fact that I need to record this stat, and then I'm recursive on ingest. And so this thing sort of at a very high level describes the program I want. But it turns out like, who cares that it's encrypted? Who cares it's a CSV file, right? None of those things really matter in terms of like describing my job to like my spouse or my friend. They don't really care about those things. They say, what is your job? I say, oh, I move this data, right? That's not to say I can run this thing, but that's sort of at a high level what my service does. And so you notice I have these member constraints. And these things are sort of saying, I have some effect here, and it has some capabilities R. And then inside of R, I have an input record, an output record, and output stats. And the idea is I should be able to transform these like high-level concepts into code I can run later. So the way to think about this is at any given point in time, I have some effects that I have not yet handled. And these are the members here. So the first thing I want to do is I want to say, oh, actually, the input records should come from some CSV file, right? The idea is I just have some CSV file, and I want to parse that thing. And for each row, I'm going to produce a record. And that thing consumes my input record effect, and it replaces it with a file provider. The next step is, oh, that thing's encrypted, right? So I actually need to decrypt that thing first. And so I run another function which sort of intercepts the file provider. And before it does any work, it's going to first decrypt it and then pass it along, right? So in the next case, I've actually added this encryption effect, but I haven't handled yet the file provider. Next step is I want to say, oh, that thing's over FTP. And so I can replace my file provider effect with an FTP effect. From there, I say, oh, I have these output records. And right now, if you look at the original code, I was just outputting them one at a time. But that doesn't sort of solve my business problem of I want to output 500 to the server per batch, right? So I have this another function which just takes my streaming, and it says, OK, I'm going to collect 500 of them and then push them off. You see that I've transformed my output of records here into an output of list of records in doing that step. And so I'm sort of collecting capabilities here, and it's sort of all invisible to my application. Next step is I say, OK, I have my output, and I'd like to push that to an API server, right? I need to make some API call, and it's not that interesting. But I'm saying, OK, I'm going to handle my record output by sending some API call. And here, I replace that output of record with an HTTP effect, right? The next step is I say, OK, I'm going to run my stats in Redis. And it's not super interesting at this point. I just sort of need to run all these effects, and those are going to happen in I/O eventually. This thing actually should say I still have an I/O effect, because I am running main. And at some point, I do need to produce I/O, right? But that's sort of it. So the idea is my original program, if you remember, was like 6 lines of code. And then I have a bunch of sort of micro transformations that I run over that thing. And each one provides some amount of functionality in terms of other effects that are sort of abstract, right? So this is sort of like dependency injection I call done right. And so that is one interpretation of my program. But I also might want to be able to test this thing without spinning up like a trillion mock service. I don't want to add an FTP server. I don't want to add HTTP. I don't want to add all these things. And so maybe I just want to be able to run this thing purely, right? I can say, oh, I have some input, and it's just got 2 records in it. This should say record here, not wrecker. And then I'm going to just run those things purely and just collect those things into a list. At the end of the day, it just gives me back the records and the stats that I produced. And then I can sort of inspect those things purely, which means I don't need to spin up mock service and write integration tests. And so sort of the idea here is if my test interpretations are correct, and my real interpretation is correct, and the program is correct under the test interpretation, then those correctnesses compose. And so my program is correct under the real interpretation as well. And so you'll notice I didn't have to do anything smart in order to make this thing testable. I just sort of abstract away all the details. And you can sort of think about doing this with our traditional tools of Monad transformers. But it's sort of tricky when you say, oh, I have all this extra functionality that I need to encode, and I need to figure out some way of batching those for any given monad I choose, right? So it is doable, but it sort of with our traditional tools, this is actually quite a hard problem. So today there's 3. This is some old slides, but there are 2 major players in the free monad space. One is called Free or Simple, which is really easy to use. It uses a lot of sort of category theoretical tricks that I don't really understand to sort of get rid of a lot of the boilerplate doing this stuff. It was friendly to use, but it was pretty slow. and it allocates a huge amount of work. I don't think performance is too much of an issue. I think we're always I/O bottlenecked anyway. But people on the internet seem to care about this, and they give me grief when I say it's not an issue. So the other option is called fused effects, which has it's got a significant amount more boilerplate. But it is very fast. It fuses away, and it can express strictly more things than you can do with free or simple. So I wrote a library and released it probably May-ish called Polysemy, and it's sort of what I like to think is the best of both worlds. It's got, we automate almost all the boilerplate away. It's a lot friendlier. We have really good error messages for when you do something wrong, and it's quite fast. So I like to think is the sweet spot between free or simple and fused effects. And so I spent a long time thinking about the performance of this, and would like to sort of go through how it works and sort of where the derivation comes from, because I think there's some good lessons to learn here. But before that, we're going to talk just sort of about free monads and sort of effects in general and how these things sort of solve the problems of what we might like out of them. So here is a program I sort of might want to build. This thing is a data structure that describes a program, but isn't actually a program, right? Sort of this is the idea of the I/O monad is a structure that doesn't have an interpretation until the runtime hits it. And so I can build the same thing here. So I say we always have this canonical example of a teletype for some reason, I guess because it's simple, but it's a little hackneyed. But so I have two options in this. I can either write a line, which takes a string, and then has some sort of recursive structure inside, right? Because I build this thing, I build this big tree that describes all the actions I want to run. Alternatively, I can read a line, and then I have some function, which is a continuation taking a string, which is the thing I read, and I can pass that further down into the teletype. So I can write a little server here, which like reads a line and then writes a line. That thing is of type teletype unit, and so we just read a line, we take that string, and we write it, and then we're finished, right? The done is just sort of there to end the recursion, but it's not very interesting. And then my slide scrolled a little bit. This thing turns out to be a monad. And we can say return is equal to done. And then the monadic substitution is sort of just push the bind as deeply as we can. And at some point, it's going to hit a done, and then we can apply the function. Nothing too interesting here. Because it's a monad, we can now write this thing, again, with do notation. And so we say, oh, I've got the same program, except now I can use do notation to construct it rather than do it by hand, right? So again, this done is sort of here just because I need to fill this thing in, and then binding will replace the done. And so this thing is a data structure, and I would like to provide an interpretation of this thing down into I/O so I can run it. So I can write this function, which takes a teletype of A and produces an I/O of A. And that thing should, whenever I ask it to write to the console, it should write to the console, right? If I have a done, I can just produce pure. If I have a write line, then I just take that message and I put strl in it. And then I am recursive in myself, and I sort of fold through this tree. Likewise for read line, where I just get a line and then can here I have this message, and I have this continuation, which, if you recall, has a string parameter. And so I need to feed in the message that I've received in order to continue processing. Is everyone still awake and still keeping track here? Cool. If you have any questions, don't feel shy to ask and just throw things at me. I'm very happy. So that's not the only interpretation for this teletype thing. I can also do this purely, where I can like provide a list of strings that the user would have typed in, and just then figure out what we would have outputted in that case. And so in this case, I have this list of strings that I am going to receive, and I have a list of strings that I'm producing. When I hit a write line, I need to sort of run myself recursively and then put that message that I would have written at the beginning of what I have received, right? So I'm sort of going all the way through and then building this thing backwards with all the message I produced. Likewise for readlining, in the case I don't have any more strings, I just assume that the user pressed enter. There's other semantics here. This is just one I chose. The nice thing about this approach is you can just write another function that chooses a different option in this case. You could crash, or you could produce something that's not just an A, right? If I do have instead a line that I like to type, then I just pass that thing to the continuation. But this is my type, right? And it turns out this done thing and the sort of the teletype recursion, these are only necessary in order to make this thing a monad. And so I can actually factor them out and then build a monad sort of more simply out of two pieces. And this thing is called the free monad, and you've probably seen it in some of Ed Komet's wild packages. These are really popular online for a while. And so the approach is for any functor f, I can sort of pull out this machinery, right? So here I've sort of encoded the recursion that used to be here. And then this thing is the done. I guess I changed its name for some reason. But now my functor is a little simpler. The teletype actions are a little simpler. And now this thing just only includes the actions I want. It doesn't have this extra like done thing. It doesn't have this extra recursion. Turns out free of f is a monad whenever f is a functor. This part isn't too interesting, but it's true. And so I can actually write some helper functions, which will construct these things for me. So the idea is these are just sort of smart constructors that massage the type into the right shape. So I've got write line and read line, which, as you notice, sort of produce the right types at the end of the day, right? The read line will return a string, and write line will produce nothing, or a unit. And when I have these, now I can write echo. And if you didn't look at the type signature, this thing really and truly looks like it's doing I/O, right? This thing just looks like real Haskell code. We're not actually doing anything, though, right? We're just building this tree, and it doesn't mean anything. This thing is purely syntactic at this point. But once we've done this work, we can factor out the evaluation, and in doing so, sort of write a lot of that recursive stuff for free. So in this case, I have some free of f, where f is some functor that I care about. And then I have some natural transformation. For any f of x, I can produce that an m of x, right? So m is the eventual monad. In this case, it's probably I/O, but it doesn't need to be, right? And then I sort of just plumb through, and I just stick, I just run this function whenever I can, and I continue producing actions in m. What this does is it means I can run teletype and I/O much less boilerplate, right? I say run free, and then I just pass in this lambda case, which matches on each of my possible actions, and then does the right thing, right? So this is just purely a natural transformation from teletype into I/O. At the end of the day, I sort of still need to produce the k, but this thing is no longer a continuation. It's just some value I need to give back. And this is sort of well and good, right? All of this sort of works, except you also would like to be able to, if I want to build like big applications out of these things, I don't want to have to like build this bespoke effect of like all the possibilities for any time, right? That's sort of the problem with I/O, is that it's too big. There's too many effects in there, and if there's too many effects, we don't really know which ones we want at a given time. So it's really nice that we can build these things sort of as we go. And the idea is we have this sum functor, which takes a functor f and a functor g. And then there's two data constructors, right? There's the left constructor and the r constructor, the right constructor. If it's left, we know we have an f inside. And if it's the right, then we know we have a g. And this thing is a functor if f and g are both functors, right? In that case, you just f map into whichever one you have. But you remember that the free monad is a monad whenever f is a functor. So we can, because sum is also a functor, we can sort of use sum to build arbitrarily sized functors and then get a free monad over that. So in this case, I've written teletype with bell, where bell rings the bell, presumably, or it doesn't really matter. We could ignore it. It's just, again, it's just syntax. It has no meaning. The meaning sort of only comes from our heads. And so I can change my implementation of write line, right? The only thing I've changed the type here. And now I've needed to stick in this L. But besides that, nothing has changed, right? And then the ring bell, I need to produce an R. And so this allows me to run actions in both of these effects, right? Here I can read the line and then ring the bell. And those are from different effects. But now I can mix and match them into the same monadic code. There's an interpreter for this thing, which is if I have an algebra that runs over any f into an m, and I have an algebra that runs over any g into an m, then I can compose those things and get an algebra from a sum of fg into m simply by just choosing the right algebra to run, right? I know it's either a left or a right, and so I can just pull the right one and run it. Is this making sense to everybody? Cool. And because this sum is a functor over functors, that means I can nest them arbitrarily, right? I can put a sum inside of a sum inside of a sum, which means I can add as many types as I'd like to this thing. I can get an effect that's as large as possible, or as large as I desire, by just sort of nesting these things together. Which brings us to the next idea, which is sort of, we want to build these like effects a la carte, and it'd be nice if I could sort of compose them automatically without needing to write those smart functors that say, or the smart constructors that say like L of R to like get it into the right place in the tree. So at a high level, we want to produce a union of R, where R is like a list of effects. And I'd like to be able to say, like, this thing is sort of a generalized either. It's got something in it, and I don't really care. I know it's one of them, but I don't really care which one. So I have this R parameter, which is a type level list. And here I'm saying I have some union where it's either a bell, or it's a teletype, or it's a state, or it's an error. I'm not really sure, but sort of in the same way that I can build this nested either case out of big sum, here I'm just sort of sticking all of those into one type. The construction of this thing isn't all that interesting, and it's sort of beyond the scope of this talk, but we can talk about it later if you're interested. But again, this thing, for exactly the same reason. This thing is a functor if every type here is a functor, right? Because we might be any of these of A, and so again, we just F map into the right place for whichever one we have. And so we can sort of reify this notion into this member class, where we say, if I can say F is a member of R, right? R is sort of the list of all possible things it could be. And I know that if F is a member of that R, then I should be able to take some F and produce a union out of it, where I just sort of forget that it's an F and remember that it could be one of any of these things. So the corollary, or the other direction, is if I have a union, it may or may not be an F, right? I'm not sure what's in it, but I know it could be an F. And so in that case, I would like to like sort of inspect what's in there, and then if that thing is indeed an F, I can give it back. But it could be something else. So if I have this, instead of writing sort of hard coding this position into the tree, now I can say, oh, actually I just have this member of teletype, right? I just know that I have some functor R, right? This big union. And I know that I know teletype is in there somewhere. I don't really care where. I'm just going to delay that decision and let the programmer decide that when they tell me how to interpret this thing. And so the only difference is I change this L into inj, right? Inject. And that says take this thing and then stick it wherever you need to stick it. And then this just works. And so all of a sudden now, this thing is purely mechanical, right? Now I don't need to know any structure in order to do this. I just produce this thing, and I just say inj. And this sort of works. I can sort of build these things through template Haskell, which is what Polysemy does, or you can sort of write these by hand, and it's not very much work. So we're polymorphic in our capabilities, right? We now say, I don't really care. I just can add constraints as I go and to describe the shape of this thing. And so all of this is sort of the state as it was a few months ago. And now free or simple and fused effects make two different decisions. So I want to cover both of them, show you what trade-offs they make, why they're good, why they're bad, and then how can we combine them back. So free or simple tries to get rid of this boilerplate, right? There's a lot of boilerplate where I need to like write these functor instances. I need to sort of write those smart constructors to say inj in the right place. And then fused effects goes on the other way to like, there's some things you can't express with the free or simple model. And it's also quite slow to like also have this bind that always pushes all the way through. So those are the two options sort of we can go from there. So we'll talk about both of them. It's unclear how to do this, but it is doable. So rather than embedding these effects, sort of building this big nested structure, what we can do is sort of just keep a queue of them, right? We just sort of, rather than sort of nest them all the way, we just say, I have this list of effects I'd like to run. And because they can't, you can't nest actions inside of each other, you can't express something like catch from monad error, where I say, I'd like to throw an exception, but if I've thrown an exception, I'd like to catch that thing. Because I can't express that sort of nested relationship, eventually I just have this sort of sequence of actions I'm going to run one after another. And so I don't actually need to build this tree. I can sort of build a queue where I can just snock and cons on that thing. So rather than this, I write sort of this. This thing is not entirely true, but it's a good intuition. There's a little magic to like get this message to be in the right place, but not particularly interesting. And so if we can encode this, we can get rid of the k. We used to have this this weird continuation thing, right, where this thing was sort of recursive, and we would interleave it with the free monad, and then the free monad would give us recursion, and this thing would allow us to build this tree with continuations all the way through it. But we don't need to do that anymore, because now we can just write a gadget that just describes the result type we'd like. So there's sort of an odd encoding here where this read line produces a string. But the way I express that is I say I have taken a continuation that like receives a string, right? So it's a little clearer because I can write it here. I just say this thing returns a string. And this looks a lot more like the smart constructor would, right? Likewise, for write line, this thing produces a unit and just takes a string. And so this is a lot easier to think about, I think, right? There's less sort of mental gymnastics you need to do in order to rewrite one as the other. Also, we don't need to write functor instances because, again, we're just going to build this sort of queue thing, and that thing doesn't require us to fmap anywhere. So we're just building this data structure, but it's sort of simpler. It's a really nice change. And it turns out this thing is asymptotically faster. Unfortunately, it's got like really huge constant factors, and so it's slower in practice. But if you had like 1 billion effects, this thing would be faster than traditional encodings. And so a long time ago, Lixia, or Liaozia, brilliant researcher, suggested that maybe we can use the final encoding of the monad, and that thing doesn't need to allocate along the way, which is where the constant factors from Fourier simple come from. I need to like allocate all these data structures and then sort of allocate a queue that like type aligns them, and there's just a huge amount of allocation, which is where all those, where the constant factors come from. So instead, I can sort of write this thing where I sort of, for any m that you want, I've sort of encoded this thing. And Lixia just dropped this on me, and I didn't really understand what's happening, but it turned out to work. And so part of this was trying to figure out what's going on here. This thing turns out to be the church encoding, if you're familiar with those. And if you're not, we'll talk about it. But
sorry, what was that? What's it called?
the church encoding.
Oh.
Yeah. And so I have some. So like a free monad is this sort of reduction to a monad, to some m. And that thing takes a continuation, and that thing is sort of that algebra that reduces a union into an m. And it's like, this puzzled me for weeks. And right, like what's going on here? But because I have this like run free thing, which takes a free monad and evaluates it in any monad I choose at the end of the day, this thing is like uniquely describes the free. This thing is, my category theory is pretty crap, but it's like the universal construction of like what makes a free monad free. So because I can provide this function, this thing says, I have this structure, and then I can produce any other monadic structure out of this thing. So there's sort of like the least structure necessary here, right? And so I can, if I just like move this free thing first, then this thing is exactly the type that I was given, right? So we're just saying the type of run freer takes a freer, and then all these other actions and produces an m of they. But at the same time, that thing is completely equivalent to this. It's maybe a little less clear, but these things are completely equivalent. And I find it always a little tricky to think that you can just stick extra functions inside of a data type, but the data type itself encodes some information, regardless. So it took a long time to figure out what's going on here. But like when I implemented this in Fourier Simple, it made things 35x faster, at least in micro benchmarks. And the question is why, right? Like what is this magical encoding, and like what does it do, and why does it work? And to do that, we need to talk about reader T, right? And so reader T is sort of the same idea. I have this m, and at the end of the day, I'm going to produce an m of a. But I also have this r that I'm threading through at every point in time. And this thing is sort of zero cost, right? This thing optimizes away because it's a new type, so it's not really interesting. And the r is statically known everywhere. So I can just sort of statically know this value and just push it all the way through. And the inliner will just use this knowledge and stick it in. So it actually looks really familiar to this run freer thing, right? The difference is I have what used to be r in reader T is now this sort of continuation describing like how to produce an m out of a union. And sort of this is the high level idea here, right? This is the interesting part, which is at any given point, I'm just passing along this like statically known function, and I'm just going to inline that every time I need to use it. And so the freer is actually just reader T in disguise, which I thought was pretty neat. They have identical monad instances. I think that I renamed some types for some stupid reason. NT and R, but besides that, the instances are identical, functor, applicative, monad. And that's pretty good evidence, right, that these are the same thing. And because we have this natural transformation, I can, whenever I have an f of a, I want to produce this freer thing, and I just say, OK, I need to inject my action. Oh, I'm going to ignore that. I'm going to inject my action. That thing gives me a union. And then I have this natural transformation, right? And that natural transformation will take a union and produce a monadic action. That's this thing here. And so I can just take that thing. Now that gives me an M, right? That's any M I want. And then I just wrap that thing in a new type. And so this means, like, at any given point, I'm not doing any work here, right? I'm just always producing the eventual monad I want. And the compiler is smart enough to inline all these things. So rather than calling ing and then done, or whatever the constructor was, I just call lift freer. And now this thing is surprisingly fast. This thing is just asymptotically better, just from this new type trick, this natural transformation trick, right? So anytime we want to do any work, we just immediately run in the final monad, and then we keep track of that all the way until the end. So there's like not really any abstraction cost here. So yes, and so at the end of the day, I just have the exact same thing, right? I call run freer, which is the way I can get out of the new type. That's my deconstructor for the new type. And then I just give it the exact same algebra, and this thing just produces an IO action. So the transformation is sort of this, right? I can inline my echo function, which is this. And then I can inline both the definition of read line and of write line, right? And those things are lift freer of those injected actions. And then I can replace sort of the bind with, or sorry, I can replace lift freer with the definition of lift freer. And that thing is to produce a freer new type wrapper with the continuation I want. And then I'm just going to run that continuation on the types I have, right? So in this case, I get the thing and I run it immediately. And so that means sort of because I am running with run teletype and IO, that's the new type I'm running, or the natural transformation. And here I just inline that thing, right? And so now I have this inline. The next step is we can inline the definition of run teletype and IO, which says now I have these case statements. And because this case is statically known, GHC will actually get rid of this case statement for me. Because it's a case of something statically known, it just replaces this with like the definitions. And then those things get statically optimized away as well. So at the end of the day, like really and truly, I'm just running IO. And the compiler is like smart enough to optimize all this stuff away, even though I'm doing all this like crazy abstraction. But I'm not, like the code I'm running at the end of the day should be just the IO, right? I've expressed it differently, but it's still the same code. And amazingly, the compiler is smart enough to figure this out. And so that solves the boilerplate and the performance problems on the Polysemy, or on the free or simple side. But on the other side, we have this fewer effects thing. And I'm running out of time, so I'm not entirely sure we'll get through this. So if you have any questions, we'll get to it and just sort of throw them at me. But so if you recall, this is sort of where we left off, right? We have this free structure, and we have these functors. And sort of this is what it looked like before we went down the one trouser leg of talking about free or simple. So we'd like to be able to express this error effect, right, where we have the ability to throw an exception and then to catch an exception. And we only want to run like this sort of continuation if we threw an error, right? You can sort of encode this in simple freer by writing this thing not as an algebra, but sort of as a separate effect that calls that like takes an action and runs it. But it turns out that is not a particularly good approach. And so because we have this embedded freer, there's no clear way how to encode this into our algebra. So we'd like to be able to write this thing, right? We have some functor that takes an exception and a k, and then produces a catch. But like, it's not clear what to put here because this thing is like a free of r, but we don't know what r is, and we don't have free. So sort of there's an obvious solution, right? Which is we just stick r in there, and we stick it in, and we say, OK, it's a free of r. And then we can go there. This idea sort of shows up to everybody who thinks about it, but unfortunately it doesn't work. And the problem is this is an infinite type, right? Because R sort of needs to describe error, and so now error is sort of self-recursive, and this just doesn't work. So the idea instead is we just give it some other type variable, some m, This thing is a monad, and we don't care what it is, right? We just say we have some monad which is self-recursive, and we'll just put it here. So this thing works surprisingly well. And then when we actually build one of these things, we just force M to be free R, and then that sort of ties the knot. So now I have this lift free, and I say I have whenever action, as long as that M is a free or R, then I can lift F into a free R. So it ties the knot. Is it making sense? I'm going to take that silence as a yes, but so the good news is you don't need to use M if you don't have to, right? State effect doesn't necessarily need anything, right? You can just get and put. In MTL, it also has this local action, but we'll just ignore that for now. So you don't need to call M if you don't want to. But if you have state and error, then we have this problem where sort of they interact badly, right? If you have this monad transform idea, sort of the way you nest state versus error, if you have a state and then an error, or an error and then a state, the state and the error sort of are in different places relative to each other. And this, we'll see this like, if you throw an exception, sometimes you'll get like local rollback. You will not see the state changes that happen in a catch block if you threw an exception. And that's if you have a error T of state. If you go the other way, then your state is persistent globally. We'd like to be able to express both of those things. So instead, so this is based on the work of Nick Wu. It's called effect handlers in scope. And the idea is we need to encode some piece of state, and we need to sort of existentialize that thing, because we're not entirely sure at any given point how many effects we've run and what state we need to hold on to. So the idea is we have some functor, but it just has some piece of value, but it's in a context. And like the context we don't care too much about. If you just purely have a functor, you can't do anything except replace the values, right? You can fmap, but you can't inspect the outside structure. So if I have this like for all f, functor f of unit, like this thing is just some context, but with no information inside of it. And so this thing will like store things for us in a way that means I can never touch it, but it means I can propagate through it. And it buys this fact, and we can just pack all the state of the world into some functor that we don't know about, and use that for information passing between effects. And the way it's sort of presented here is we have some sort of state token. This is F on the last slide. And I say, I have some piece of state that I want to keep track of, but I'm not going to show it to you. So that thing is a token of unit. And then I have this function, this weird function here. And I say, I have some, if I can distribute this state through some action, right? I have some m of x sort of wrapped inside of this world. And then I would like to produce an n where I've sort of pushed the state inside. And so I've sort of done one layer of computation. At the end of the day, I have some effect of m and a, and I'm going to produce an effect of n of token of a. And this is a little weird, right? It sort of gets clearer. I don't know if I have a slide on this one. So sort of these are what these things mean. But it's sort of clear if you think about m as like the freer of R. I've got some set of like actions I can perform. And then n is the same set, but a little smaller. I've handled one of these effects. And in doing so, I might have produced some state that I need to hold on to, right? When I call run state, I have, at the end of the day, I get like the last state I need to hold on to, right? I can push that thing. But when I call like run error, I have either the exception or I've got the value. And so those are two pieces of state I need to sort of thread through. And the idea here is I can encode both of those things as some functor tk. In the case of state, it's like s of comma. In the case of either, in the case of error, it's an either of the error. And so in doing so, I can handle one effect into like a slightly smaller set of effects by just removing one of those effects and pushing it through. And in doing so, I collect some piece of state. And so I can sort of compose these things together as I go, and I can build more and more state, which I can thread through even if I don't know what it is. And so having a weave, or like this effect instance for my effect, having a weave allows me to push other effects through me. And so if I can produce one of these things for every effect in my stack, that means they all compose in a way that like MTL sort of does if you provide like a monad state and a monad error and a monad lift and like all these weird monad things, right? It sort of reduces the problem of O of n squared instances that you have in MTL down to O of n. So asymptotically better. Finally, so I can implement this thing for error, right? I can say, OK, so whenever I need to throw an effect, I just throw an effect. And I don't need to do any weaving because this E can be of any type I want, or the result of this thing is anything. So I don't need to do any work. And then I just write this stuff. And I sort of just made this type check. I just didn't really know what I was doing. I put underscores until it worked. And I describe that sort of like a bad idea, right? It's if I don't really understand how to do it, but I have to do this for every effect, that's not a good user experience. I'm really low on time, so I'm going to just jump ahead here. And here's so I can sort of do this thing, and eventually, if you go through all the work, you can automate these things away. It turns out there's a free effect, which is this gadget that sort of composes magically all the state you want. And sort of the insight there is we can just build this thing instead. One last thing I'd like to talk about is this this neat trick where if you have this recursive function, GHC will usually make it slow if it's self-recursive. There's this idea of a loop breaker where you don't want to inline a function into itself because that thing will be infinitely large. And so instead, you sort of need to find one function in a set of mutual recursions that is sort of like the least interesting. And then you call that the loop breaker. You inline everything else, and then you can still break the recursion. But we can sort of do this by hand. There's a problem where if you're self-recursive, then there isn't a loop breaker, right? The only function you have is yourself. And so you can't really simplify, and the simplifier just like will not run for sort of interesting cases like this. And that turns out, even though we've got all these clever things, it means we're still slow in practice because we're not getting all the optimizations that GHC promises us. And so we have this dumb trick, which is rather than being self-recursive, I can say run state is implemented in terms of run state B. Run state B is exactly the same thing, which is in terms of run state. And I just marked that the first one is inlineable and the second one is not inlineable. And then this one gets chosen as the loop breaker, and this one will get simplified. So that's a little weird trick. I don't know if this is always going to be in GHC, but it does work today. And there's a nice plugin called Loop Breaker, which will implement this for you automatically. So I think I'm out of time. But if there's any questions, I would love to answer them for you.